Hello and welcome to Lecture 2 of Magnetic Forces and Fields in Phys 1201. We spent some of the last lecture looking at how we figure out the direction of a magnetic field. In this lecture, we're going to look at how we figure out how strong a magnetic field is. We saw a rather imprecise statement about magnetic field strength in the last lecture to do with how quickly a compass needle comes back to pointing in the direction of the B field, but we need something better than that. We can't use what we did with E fields, where we use a probe charge, because B fields don't exert forces on stationary charges. They only exert forces on moving charges. Well, that means they exert forces on currents in wires, because that's all a current in a wire is, moving charges. So here's an experiment you can do to determine the magnetic field strength in a location. You already need to know the direction. Well, you can get that with a compass. Now you run some wires in parallel to the field and a piece of wire perpendicular. And the first thing is that the B field exerts no force on the currents parallel to the field. We'll come back to that later. For now, it's just convenient because it means we can ignore these pieces of wire and only focus on this piece that's perpendicular to the field. And then we find that the force on the wire, due to the B field, is proportional to the current through the wire. Also, if we use a longer segment of wire that's perpendicular to the field, we find that the force is also proportional to the wire length. And so now we have a definition of B field strength. We can measure the magnitude of the force on a probe wire, not a probe charge, but a probe wire. It has to be perpendicular to the field. And our B field strength, no vector symbol here, this is a magnitude, is just the strength of that magnetic force on the wire divided by the current through the wire and its length. Now that we have a definition of field strength, we can define the unit of it. The unit of the B field is called the Tesla, T. And you can now see what it is, because a force is in newtons, a current is in amps, and a length is in meters. So a Tesla is a Newton per amp meter. The Tesla is a pretty abstract unit. We don't have direct experience of it like we do with, say, meters and seconds. The thing to note is that it's big. You don't very often come across a full 1 Tesla field. Earth's magnetic field is typically in most places, about 5 times 10 to the negative 5 Teslas. A fridge magnet right at its surface has a field of about a millitesla. A rare earth magnet will produce a full Tesla, so that tells you that's a strong field. If you've played around with rare earth magnets, you know they're strong. And similarly, inside a hospital MRI machine, the field is about a Tesla. If you want stronger fields than that, you've got to look in places like the Large Hadron Collider, where they generate 8 Tesla fields. So now that we have a meaning for magnetic field strength, we can start looking at how to calculate magnetic field strengths due to various objects. So we've already seen that a straight wire produces a B field, and we've seen how to figure out its direction using the right-hand rule. The strength of the field decreases with the distance, and we're going to call that distance r. And you can see that if you hold a compass near the wire will influence the compass, but if you move the compass farther away from the wire, then the magnetic field of the Earth will take over, and you won't see any influence from the wire. For a very long wire, and really what that means is an infinite wire, but you can take it as being any wire that's long compared to the distance away from it that you're looking, the B field due to a wire is mu naught, I'll talk about that in a second, times I over 2 pi r. So that I is the current in the wire, and that r is the distance from the wire of the point where you're calculating the field. This mu naught is another universal constant. It's called the permeability constant, and it is 4 pi times 10 to the negative 7 with these units. Note, it's exactly 4 pi. That's kind of curious, but for your purposes, you'll most often just want to use it as about 1.26 times 10 to the negative 6 Tesla meters per amp. Let's calculate a field, and let's do it for a pair of wires. So B fields are going to add together just like E fields will. You have to do a vector addition. And these are nice long wires, so we can use this equation that we've seen for the B field due to them. And so now at point P, where we want to know the field, there are going to be two contributions, a field due to wire A and a field due to wire B. Let's get the directions first. So if you curl your fingers of your right hand around this wire, sticking your thumb in the direction of the current, you're going to conclude that the field is out above the wire and in below it. And so there is a field that I'll call BA into the page at point P. Similarly, you have this for this bottom wire, and so there's a field out of the page that I'll call B here. And so our B total at P is just the vector sum of BA plus BB. That means I'm going to have to define some axes to carry out a vector addition, although this is going to be a nice simple vector addition, right? The fields are in opposite directions, and so I'm going to have a simple subtraction here, but let's go through it. So I'm going to say then my BA, which is into the page, is some negative a magnitude BA hat, and my BB then is some positive a magnitude I hat. And so my B at point P is just going to be some BB minus BA all I hat. And I can write that in terms of the currents, so I'll just say my BP magnitude, and I'll write it in terms of everything else. Where this RA and this RB are both just a centimeter, because we're looking halfway between. So I'm just going to say RA equals RB equals R, and that's a centimeter. And I'm just going to simplify this a little bit just to make my plugging in a little easier. It ends up coming out like this. This is an optional step just to simplify the plugging in. Okay, well, you might want to use 1.26 times 10 to the negative 6 for mu naught, but look, there's this 2 pi down here, so it's actually going to turn out nicely if I use the exact value of mu naught. And at that point, you can practically do this in your head, because this cancellation means you just have 2 times 10 to the negative 7 over 0.01, 2 times 10 to the negative 5 times negative 2, so negative 4 times 10 to the negative 5, and look at the units, meters, amps, and we just get Teslas as we should. And so our B field is into the page, negative 4 I hat times 10 to the negative 5 Tesla. In practice, you make stronger fields with loops than you do with straight wires, and so that's what we're actually more interested in most of the time. Let's look at some loops, and we'll start with this square loop, because you're used to thinking about straight pieces of wire by now. So if you curl your fingers around this top wire, and I'll number this 1, 2, these wire segments, I'll number them this way. So if you curl your fingers around 1 with your thumb pointing to the left with this current, you're going to come to the conclusion that the field is out below this wire 1 and into the page above it. And so there's a field near the center that is out of the page due to wire 1. I'll call that field 1. Similarly, do the same thing with this wire. Now your thumb is pointing down and you're curling your fingers around this wire, and you again come to the conclusion that the wire is in now to the right of this wire and out to the left. And so there's a field in due to wire 2. Do the same thing for 3, you're going to come to the same conclusion, and for 4. And so all these inward fields are adding together, and that's going to be true everywhere inside the wire. You're going to get these fields adding together, giving you fields pointing into the page, and because the fields due to every piece of wire add, they're quite strong. Now, if you look, say, over here, the field due to wire 2 here is into the page. And we're quite far from wire 2, so this is weak. The field due to wire 4 here is into the page, and we're closer to it, so it's strong. And so overall, the field is into the page, and there's a cancellation going on, so this is pretty weak. And you're going to come to the same conclusion everywhere else. The field then, for this direction of current around the loop, is out of the page and strong inside the loop, into the page and weak outside. You can make all the same arguments for a circular loop, and so for this direction of current you find a strong outward field inside and a weak field into the page outside. Let's see that with a real coil. So you can see here the current comes out of the source here in at this point, and you can see this yellow wire comes this way, and so the current is running counterclockwise in this coil. And now the compass shows you that the field is out, which you can confirm with the right-hand rule, just like we did. And if I flip the coil around, now the current is going clockwise from our point of view, and you can see that the compass was showing the field points in. In the vicinity of a loop, the field varies quite a bit from place to place. It's strongest inside the loop, in other words, in the plane and inside. It's also pretty strong out on the axis of the loop if you don't go too far away. On the other hand, it's very weak outside the loop, as we already saw, and in the plane of the loop, outside the loop, it points the other way. Where it's strongest is at the very center of the loop, and there the strength is given by this formula, where that capital R is the radius of the loop. And that's true really only at the very center, but as long as you're close to the center, this will be about right. The real reason coils, or loops, are so much better than straight wires for generating strong magnetic fields is that you can loop your wire around many times and get all those B fields just adding up. So this is the B field due to a single loop of wire, but when we talk about a coil, we mean that the wire comes in and it goes around the loop many times, and then it eventually has to go back out. And so we would say that we have n turns of wire, just the number of times the wire loops around, at which point your B field due to your coil is going to be just n times what you have for a single loop. That's if your coil is like this, where everything goes around and you sort of have a thin circle. But often what you have is that your wire comes in and it loops around, and you have your wires go like this. So you have a long coil. And so now it has some length, L. This is not what we call a coil. This is what we call a solenoid. And the B field due to a solenoid is a little different. It's almost the same equation. It's Ni here, but then you divide by the length. And this is strictly only true if it's very long compared to its radius. If it is not long compared to its radius, but it's also not nice and thin, so you can call it a coil, then you're in some intermediate case, and neither of these formulas will work exactly. The one remaining thing about a solenoid that's really convenient is that the B field inside a solenoid is very uniform. It doesn't vary much as you move from side to side or along the solenoid, as long as you stay well away from the ends.